I'm going to put up here for you guys so you can grab them. Sorry,
Nice.
I'm a little bit crushed in my bag. So with your lab notebooks, there's a little sheet inside that kind of tells you what was graded and how many points there were. I mean, if you didn't get any points marked off, I just wrote the total points for each section. If you did, then you'll see where I wrote like a 0 or I took a point off for a certain area. I made it out of, let's see, online it had said 30 points, and on the syllabus it may have said 30 points, but I decided to make it out of 40 points. Just because there was enough information and points, and I haven't been giving you points for attending like lab, but I've been going through the sign-in sheet, so I just decided to make this worth more points to really give you guys that opportunity. The good news is that you guys did a really great job with your notebooks. I don't think there was anyone under like 36 points out of 40, so that's actually really good. I've never had a class where everybody's doing a great job on their notebook. But you guys are really doing an outstanding job with everything, and so I really appreciate that. Especially because you guys are doing this in an accelerated format. So if you want to come up and grab your notebooks, go ahead, just so you have them, so you can start writing down everything. And then I will start the PowerPoint. Okay, so today we have a few things to do. And Albert, you have gels? Okay, because there's not going to be enough time to pour gels today. I don't think so. I just feel like diluting, getting them set up, and loading 2 gels, I think will take the whole time. So go ahead and we'll give them gels today. And we'll,
Today's the 1st of July.
okay, so we have to do a few things today. Today we're going to actually use the math that we practiced last week, diluting concentrated stock solutions. So hopefully you did the homework, you feel a little bit more comfortable with that, because today you actually have to do the math and make a dilution. And so the reason why you need to do a dilution is because we're going to run we're going to do some agarose gel electrophoresis, and I'll tell you what that is. And in order to do that, we store the buffer as a concentrated stock, so we can have a smaller bottle. It's 20 times concentrated, so it's at 20x. So you guys are going to need to dilute down to 1x. Okay, you're going to need to make 1x SB buffer. This is a specific type of buffer that we use when we're running DNA gels. Okay, there's a couple of different buffers. We're going to use this one today. So you guys are going to have a 20x SB buffer, and so you'll have 20x SB, and you're going to need to dilute down to 1x SB buffer. In the lab, I wasn't sure what size of bottle Albert was going to give you, so I put 0.5 liters or 1 liter, but he gave you a 500 milliliters, so that's the 0.5 liter bottle. So you'll make 500 milliliters total. So 1x buffer, and you need 500 milliliters total water. Okay, so that's going to be the first part of your lab, is just using the formula. What's the formula you're going to use to dilute this concentrated buffer? Good. You're going to do C1 V1 equals C2 V2, and you're going to be solving for V1. Okay, remember V1 is the amount of your concentrated buffer that you're measuring out. Okay, so you're solving for V1. That's going to give you how much of this 20x buffer you need to measure out. And then to make the solution, what do you need to do? How are you going to make the solution? So that equation tells you how much of your concentrated stock, right? V1 is going to give you the amount of your concentrated stock buffer that you need to measure out, right? How much of that 20x you need to measure out. But you're making a dilution. So what else do you have to add to this to dilute this down?
Distilled.
You're going to need to add distilled water. Okay, how much distilled water? Well, you're going to get this amount, and then you're going to subtract it from the total. So the total volume that you need is 500 mils, right? That's your total volume, so that'll be 500 mils total, right? And so you're going to need to take 500 mils, and you're going to need to subtract the amount of concentrated stock from that, so that you know how much water to add in. Does that make sense to you guys? So subtract the milliliters of concentrated stock, and this will give you the milliliters of the DiH2O that you need to add in. Does that make sense? Okay, and then you actually need to measure everything out and make your buffer. So Albert's brought out the 20x stock solution, which is here, the 20x SB. Okay, when you're using this buffer, never pour anything back into this stock bottle. Okay, never pour anything back, because you might think you're pouring back the concentrated buffer, but what if you make a mistake and actually pour water back in here? So once you take liquid out of this bottle, if you get too much, don't pour it back in. We'll just have to discard a small amount that you may have taken out, okay? So even if you take a little bit of excess, that's okay. I just don't want anything back in. So this is your concentrated stock. Albert's given you a bottle, which is here. In the instructions, it says to get tape and label your bottle correctly with all pertinent information. So you'll get a piece of tape, you'll put it on your bottle. What information should go on that piece of tape? Date, what it is, its concentration, so it'll be at 1x. Initials, and you should probably write Bio 190 like summer, okay, just so we know which class made them. It's always helpful for me so that when I go through I can see what's going on. Okay, so you'll have your graduated cylinders, because you'll obviously need a larger graduated cylinder to measure out your distilled water. You'll need a smaller graduated cylinder to measure out your 20x buffer, okay? Albert also brought you a funnel so that you can easily put this in the bottle and pour into the funnel so you don't make a mess. Although this has a pour spout, it can often just go everywhere. So I do recommend inserting the funnel and pouring everything that you've measured so that everything stays in your bottle. Because if anything spills out, is your concentration going to be correct? No, you're going to be off, which means your gel boxes aren't going to work. So the other piece about this is that there's no real way of me knowing 100% that you did this correctly until you actually go use your gel box. So if you use your buffer in your gel box and your gel box doesn't work, that's kind of a clear indication that something's wrong with your buffer. Okay, so if you make a mistake in this first step, then you're going to have trouble actually running your gel. Okay, so just if you're unsure and if you want us to look at your calculations, make sure you show us what you're going to do before you start measuring anything out. Please include all your calculations in your laboratory notebook. So make sure you show the math. Make sure you say how much you measured out and what you kind of did. I gave you a very general protocol, but I want you to put in your details. Just like I said, I wasn't sure what size of bottle we had available, so I left it a little bit more vague. So that's going to be step one, just making the buffer for this experiment. Okay, step two is going to be actually running samples on your gel and doing some analysis. And so what you guys are going to do today is two different things. you're going to run an analysis for a crime scene investigation. So it'll be, there will be evidence that was collected. There will be 3 suspects. So we'll have that situation. So you'll do a crime scene analysis to determine who is the guilty suspect. And then the other analysis that you're going to do is a paternity test, a paternity analysis for Honey the cat. So that's going to be the second. Both of these need some type of analysis of DNA. And to do that, you will use gel electrophoresis, which means that you're going to separate pieces of DNA out on a gel. Okay? And so have you guys ever made Jell-O before? Yeah, or seen Jell-O, eaten Jell-O? Maybe. Okay, so maybe if you've never made it, maybe you've eaten it. What does it feel like? It's kind of squishy, but a little solid, right? If you make Jell-O, you open the package, it's gelatin and sugar. You pour it into a bowl, what do you throw in there? Hot water, right? Hot boiling water. You dissolve all the sugar and gelatin. And then you pour it into whatever container you're going to use, and then you either put it in the fridge or add some ice cubes before you pour it, but it has to cool and set, and then it turns into a more solid mass, right? Jell-O mold. That's exactly how gel electrophoresis works. We use a different sugar. It's called agarose. And so you're going to take that sugar. Albert already made gels for you. I was gonna have you make gels, but I'm worried that we don't have enough time because this is a 2.5, maybe not even quite 2.5 hours compared to a 3-hour lab. And you guys are a really good group, so I want you to run 2 gels per group. So I'm gonna give you a little bit more to do just because you guys are a little bit faster, and because we have class every day, you're picking up the skills easier and you're very competent at them. But I'm just worried that to make the gels, pour them, and let them set, we're not gonna have enough time. So Albert already made gels, but don't worry, you'll be making several more gels in the future. Just today, we're gonna use the gels that are already made. Okay, so to make a gel, you would mix that sugar with this diluted buffer that you're going to be making, and we would have to microwave it. We'd have to heat that sugar to make it dissolve, pour it into this little casting tray. So that's what this is. It's like your mold, right? It's shaped like a little rectangle. And what you do is you stick this in. This is called a comb, and this makes holes in the gel so that you have little slots to actually load your DNA into those holes, okay? So these stay in there. You pour your agarose that's been dissolved in the microwave, you pour it in here, and it makes a little rectangle. You pull this out, and when you pull it out, there's little holes, and those are called the wells. That's where you'll load your DNA samples. Jell-O is very flimsy, and so are these gels. So you need to use care when handling them. They're slippery, they'll break. If they fall on the floor, they'll crumble into pieces. So just as you're working with your gels, think about the fact that they're slippery, they're slimy, and they break easily. So just so you kind of keep that in mind. All right, so let me give you a little bit more background so that you can understand what you're going to be doing. So I explained the gel to you so that you can kind of understand this picture. This is showing Jell-O gel on a slide, and these little wells or those little holes are where you would insert your DNA, okay? And you're gonna have a better idea once you see it right in front of you. And so what you will do is you will load sample into each of those wells. We're gonna have to give you kind of a demonstration. We have the little trays in there, huh? The little trays. We're gonna bring some little fake gels out for you so you can practice loading a few times before you actually load a real DNA gel. Because again, they are really soft. If you stick your tip too far into that well, they'll poke right through the bottom of it and everything will just spill right out. So there is kind of, you need to understand kind of how far to stick your tip into the well, and you have to have really good technique dispensing and not sucking your sample back up before you lift your hand out of the gel. So we want to have you guys practice a couple times in these fake little gels before you actually do the real thing. Once you feel ready to go, then I'm gonna give you guys 2 gel boxes so that you can run 2 gels. So pretty much, you know, if there's a group of 2 or a group of 3, everyone will get a lot of hands-on experience loading the gels and feeling really comfortable. So what happens is you'll load DNA into these wells. These boxes can hook up to a power source. And so you'll have this box in front of you. And it looks like this. This is called the Mini 1 Gel Electrophoresis System. And so your gel is going to sit, let me open one of these casting trays. I don't have the gels in front of me. So there's a lot of different things. I'm going to show you a video about exactly how to put this little box together. No, I don't want it. Oh, I'm sticking it in the wrong way. I'm looking for the little edges. There's kind of directionality to these little trays, so I don't want to screw it up. There we go. So this is your gel box, okay? In here, you're going to put buffer, and you're going to have your little gel sitting on top, okay? And it'll go in this little tray. And so what you're going to do, and if you notice, there's a negative electrode and a positive electrode. And this is going to plug in. So we're going to actually run electricity through this gel. There's going to be a current that's passing through. That's the reason why we use a buffer instead of water for conducting the electricity, keeping it at a proper pH temperature. If you just use water, it's not going to work properly and your gel's probably going to melt. Okay, so you absolutely need to use buffer. Don't make the mistake of going and getting water and pouring it in here. That's why you're going to make this buffer. You're going to make your buffer and you're going to use it in your gel setup. And so your step, you're not going to make the gel, but you're going to load the gel and run the gel, and you need to make the buffer for it. And so what you'll do is you'll have your gel here, and you're going to have to use your micropipette and load into each little tiny well, each DNA sample that we're going to give you. Okay? The reason that this works is, do you guys remember from lecture, is DNA negatively charged or positively charged?
Negatively.
It's negatively charged, okay? It has a negative charge because of that phosphate group. Remember, the phosphate had a lot of negative charge because of the oxygens that were attached. Okay, so what happens is you load your DNA into the wells, and those wells are closest to the cathode, or that negative electrode. Okay, and you're going to then put the lid on this gel box and turn it on, and once you put the lid on and turn it on, electricity is going to start flowing through this system, okay? And so it'll be a nice closed circuit, and so this DNA will start migrating to this positive charge, to this positive anode. Opposites attract. So the negatively charged DNA will always be attracted to the positive charge at the other end of the gel, okay? And so on the box, you'll see there's a negative side and a positive side. Your DNA needs to be loaded nearest the negative side, and it'll migrate toward the positive side. As it's moving through the gel, if there's multiple pieces of DNA in your tube, they will separate out based on size. Okay, again, that will separate out based on size. So if you're a large piece of DNA, are you going to be able to get through that agarose matrix faster or slower? You're big. Slower, there's going to be more resistance. As you're traveling through, imagine you're getting stuck, okay? If you're a small piece of DNA, you can kind of migrate through that agarose a little more quickly. So in the same time frame, smaller pieces will get through more quickly, larger pieces will get stuck sooner. I like to think of the time my kid got lost his glasses in the IKEA ball pit. Okay, that really happened. We went to IKEA, oh actually my husband took him to IKEA and dropped him off in the play area and kind of walked around. They came home, I got home from work, I said, Andrew, where's your glasses? I lost them. I was like, what do you mean you lost them? They're in the ball pit. I jumped in, they fell off, I could never find them. I'm like, you didn't tell Daddy? No. And so I'm like, oh my gosh, we need to go back there, right? Glasses are expensive. So we go back to IKEA. Can I please go in and look in the ball pit? And the employees, no, I'm sorry, adults are not allowed. I'm like, can you please look in the ball pit? It's a huge ball pit. The balls are red, and some glasses were red, of course. So like 3 employees get in, and what happens? They're big, so they jump in and they're kind of stuck, right? They're kind of stuck, and they have to kind of wiggle their way so their feet can touch the bottom and they can move around. right? They had bins and they were like digging through. Of course, those things don't go in very far. Even when the kids jump in, what happens? They they get stuck. They don't sink to the bottom. So they were in there for like 15 minutes and they're like digging around. They don't find them and I'm just like, oh no. And then all of a sudden one of the girls was like, oh, and I said, oh boy. She's like, I think I found them. And so she like starts digging in. I guess she like kind of stepped on them a little with her foot. But she didn't fully break them, and so she brought them up, and there they were. Of course, where were those tiny little glasses? They had went through that matrix all the way down, ended up at the bottom. Okay, it was a similar idea. They kind of just wiggled their way as kids jumped in, they wiggled. So the small item got all the way to the bottom of the ball pit, whereas, bigger things stay stuck on top. Kind of the same idea here. So we found the glasses, it was good. But I always think about that. Oh my God, I had to get his glasses. So if you look at this, these little blue lines represent pieces of DNA of different sizes. There's going to be multiple pieces in your tube. And so these are the larger pieces, these are the medium, this is the smallest. These arrows are showing that they're moving, they're being pulled to this positive electrode, and that's how they're separating out. And so if we look here, this is the longest fragment, this is the shortest fragment. So there's 2, 4, 6, 8, 9 fragments in that well that were loaded, and they were all separated out. So it gives you a nice banding pattern that you can see. You're gonna have that same situation today. You might have 2 bands, 3 bands, 4 bands, 5 bands. It just depends on how many pieces of DNA are in your sample, okay? And you're gonna separate them all out. And so what you're gonna be doing is a couple of things. I told you you're gonna do a crime scene analysis and a kitten paternity. So in your lab, there's different reasons why you might wanna use gel electrophoresis. And so, crime scene. If you go to a crime scene, what are they going to collect from the crime scene? DNA, and in what way? Like, what might have DNA at the crime scene that they would collect? Blood splatter, hair samples, fingerprints, skin cells, anything. I mean, one follicle of hair. We've done this in a different class, and I'm going to make you guys extract your own DNA from your own cheek cells towards the end of the class. But I've done that same experiment where students plucked one hair out of their head, put it in a tube, extracted their own DNA, and did PCR amplification for a certain segment. The same thing can be done from a crime scene analysis, right? They find a hair, that's enough to extract DNA and do some of these techniques. So you can do something called a PCR amplification, which means that you can make little primers. We talked about primers in lecture. Those are the little starting points so that you can make copies of things. You can make primers and make billions of copies of a certain section of the DNA, and then you can compare what you found in the evidence, or what you found from the suspect to the evidence, and see if those banding patterns match up. Because we all have different DNA patterns. Even though our DNA is highly conserved and most of it is the same, there are areas within our DNA that's a little bit different. And remember, we have introns that get spliced out. Those areas can be different between individuals. And so each of us has not only our fingerprints on our fingers, right, that are unique to us, but each of us has our own DNA fingerprint. So if we took your DNA and we cut it with something called restriction enzymes, they're just little molecular scissors. If we cut your DNA with certain scissors, you will get a certain pattern, and no one else will have your pattern unless you're an identical twin. Then there can be some confusion, right? If you're identical, then your sequence is probably going to be the same. Okay, so that's the only place where it gets a little bit tricky. However, you can use this kind of idea to extract DNA and then cut it up with molecular scissors and then run that out on a gel and look at the pattern that emerges from each individual. The other way you can do it is you can do something called PCR. Like I said, you can make primers and you can amplify certain regions of the DNA and get banding patterns. And so that's called kind of DNA fingerprinting, getting the pattern in the DNA for each individual. And so you're going to see how this works. So if you extracted DNA from a crime scene, and let's say it was found in a hair follicle that was left at the crime scene, and they take that DNA, they remove it from the hair follicle, they put it in a tube, they put certain molecular scissors or restriction enzymes in, and they cut it up. okay? They do the same procedure by taking DNA from the suspect and cutting with the same scissors, right? It has to be the same so you can compare the patterns. So if this was the DNA found at the crime scene, it produced 3 bands of these sizes. This was the banding pattern from the suspect at the scene. Do they match up? Are their patterns the same? No. Is this the likely suspect? No, it's completely different, right? Their banding pattern does not match up with what was found at the crime scene. So if you're doing a crime scene analysis and you're going to do a DNA fingerprint and you're going to get DNA and cut it up and run it out on a gel, every single band needs to match up, okay? Every single band needs to match up. So let's take a look at this one, okay, just to make sure you understand what you're going to do. Here was blood from the crime scene. Here's hair from the crime scene. Here it gets a little bit more complicated. Here's the victim's blood, because you need to know what the victim's pattern looks like so you're not thinking, oh yeah, this is it, and really you just got DNA from the victim. Okay, here's the husband's blood and the suspect's blood. Okay, what information can you get from this gel? Okay, so number 1, that the crime scene blood is the victim's blood. So the blood that they found at the crime scene belonged to the victim. What else?
The crime scene hair is husband's blood.
Is it though?
It's pretty similar.
So it's pretty similar, but it's missing 2 bands. So it's not a perfect match, right? Do you see that? The crime scene hair looks very, very similar to the husband, but it's not 100% identical. It's missing these last 2 bands. So maybe it's somebody that has a similar like lineage, maybe a similar DNA patterning, but it's not for sure the husband. Do you guys see that? Because those 2 bands are missing.
Could it be like anyone that their child?
Maybe it was a family member. Maybe it was somebody in close relation, but it was not. This isn't enough to say it's the husband, right? 100%. Is there a possibility that maybe the DNA was degraded a little bit and we didn't get those patterns? It's possible, so that's why you would not just rely solely on this. There'd have to be more evidence if you were gonna say. Yeah, because it's very close. One of the biggest issues with crime scene analysis is that the DNA degrades over time, and so the quality of the DNA may not be good enough to get a very good analysis. So here we cannot say with 100% certainty that it's the husband. We can't. What about the suspect? Does the suspect's patterning match anything?
No.
No. So here it's inconclusive, right? It was not this suspect. It looks like it possibly could have been the husband, but we can't say with 100% certainty. So this data is inconclusive, right? There's nothing that we can really say for sure. Okay, what about this? This is what a banding pattern might actually look like. So here's the banding pattern from the crime scene, here's the banding pattern from the victim, and here are 2 suspects. So if you look at this banding pattern and you do the comparison, you're gonna wanna look at, oh my gosh, why is it shaking so much? Suspect 1 compared with the crime scene, suspect 2 compared with what was found at the crime scene. Who's the guilty suspect here?
Suspect 1.
The first one, does every single band match up? Every single band. And notice, is there just 3 bands? No, there's probably 25 bands here. So that's a very good match. Every single band matches up. So that's why I say we each have our own DNA fingerprint when we cut DNA with certain enzymes, and every band will match up. And so this is very good. This is very conclusive evidence that it's more than likely this person. Okay? So that's what you're going to do today. We're going to give you samples. You're going to run them out for yourself. You're going to need to look at the banding patterns and determine which suspect is the guilty suspect. Yes? Can you guys do that? Let's see if there's any more I don't remember. Yeah, so that was suspect 1. What about this last one? So here, there's the blood. This blood stain was found at the crime scene. Okay, and let's just say they determined that it wasn't the victim. Okay, this blood stain was found from it was not the victim, and there are 7 suspects. Can you figure out who is guilty? Suspect 3. Do you guys see that? Suspect 3. It's a little harder to see with great resolution, but if you really look at every single band on this gel, suspect number 3's banding pattern matches the blood stain. Yes? So this is pretty straightforward, as long as you know, really like I said, the limitations are extracting the DNA. If you get data from the crime scene, there's a lot of procedural work. Did you collect the data in a lawful manner? Because sometimes you have DNA evidence, but it's not admissible in court or usable in court because of the way it was collected, right? We've seen that with a lot of high-profile cases. Think about O.J. Simpson case, right? A lot of that data got thrown out even though there was a lot of DNA evidence that was collected because of the way it was collected and handled after collection. Okay, so one of the things that, I mean, I started watching, you know, 20th anniversary was last year, so I started watching all the stuff again, and one of the shows is on Netflix again. And so anyway, they were talking about how the body of Nicole Kidman was covered with a blanket from her home because the officers were trying to be respectful because there were so many, you know, paparazzi news there taking pictures, and they thought they were doing something respectful, but they covered her with a blanket from the home instead of, you know, a blanket or something that they brought that was sterile, that they opened and they covered her with. And so one of the arguments was like, you know, yeah, the DNA from whoever they potentially was the suspect could have been on that blanket if they had ever been in her house, and maybe that's why the DNA got on her body, right? And so that was a huge argument right there. Not only that, like the police officer that collected a lot of the samples didn't drive to the police station and submit the evidence immediately that day because they lived somewhere else and they were close. The idea or what they said was, oh, you know, the crime scene was here, I lived here, the police station was all the way back over here. I just kept the samples in my car, went home, and then submitted them the next morning into evidence. Can you do that? No, so then there was all this like, well, were the samples were they tampered with? What if they were mixed? What if stuff was planted in that evidence? Yeah. So I mean, that kind of thing it's critical that you go through the procedural steps, because then the biology, right, the DNA evidence isn't going to help you, even if it's there. Okay?
Even if they like got evidence without like a warrant or probable cause, all that's thrown out.
Yeah. So it's really important that every every step is followed to the T, or you're not going to be able to use the evidence. Okay, so the other gel, so that's going to be one gel. We're going to give you a set to analyze from a crime scene. So you guys are going to have 2 gels running per group. We've never done this before, but I think you can do it. I think you can do it. I'm confident. I'm very confident in you guys. And so the second gel that I want you to do is another use of DNA gel electrophoresis. This is for paternity, right? You guys watch Maury or, you know, none of that. Back in the day, that was huge, right? They bring out like, oh, who's the baby's daddy? And it was daytime television, but it does require DNA. You need to go and take a swab from the child, then you need to take a swab from the mother, you need to take a swab from the potential fathers, you need to extract the DNA, do some analysis, run a gel, and get some information, okay? And so, the way paternity works is that if you think about genetics, people inherit their DNA from who?
Their parents.
Parents or male and female. So there's a contribution, 50% male, 50% female, that was contributed to that individual, okay? And so what you have to do is you have to look at the child's banding pattern, and you need to compare it to both the mother and the potential fathers if you're trying to determine the father. Right, obviously the mother knows that she's the mother, okay? Unless you're a surrogate, in which case you might not know. There was recently a case where a woman was a surrogate to a family, so the fertilized egg was implanted, and she was supposed to carry the child. And normally, once an egg is implanted, you're not supposed to get pregnant, right? Usually that's it, and so, but the process, because it wasn't natural, they put it in there. And so she also landed up getting impregnated by her husband at the same time. So the woman goes and she has twins. They tell her she has twins. She knows she's carrying twins. She just assumed, because they implant multiple eggs, that they were both from the surrogate, the family, right, that she was caring for. When the babies were born, it was obvious that one child was not theirs and the other child was, because of ethnicity, race of the couples, okay? So the couple, yeah, one of the babies was African American, and so dark skin, and the couple was Asian that was going through the surrogacy. So there was an Asian baby, and then there was the other baby. And what happened, there was a huge legal battle because they let the couple take both babies, and they didn't give the person their baby. So they actually didn't have their baby for like several months. They had to go to court and fight for these rights, even though it was actually their child. But then because of this agreement, crazy stuff, right? So crazy. Yeah, I read that one, like it was, I think it was mid or end of last year. And it was just so bizarre to me to think that they wouldn't just say, okay, yeah, this is obviously your child, you know, DNA evidence shows, you don't even need a DNA test to see this. But yeah, I mean, they could do a swab, and within a day, they would know exactly who the parents are. A blood test could very preliminary show you who the father and mother are. But the fact that this couple actually took the second baby.
They didn't question it? Like...
They did, they took the baby, and I mean, I think it was obvious, but I don't know why. It was, so, the child is here. These are the potential fathers, this is the mother. And so what you're going to do is you're going to have to compare each band from the child, and every band must either match a band in the mother or a band in the potential father. So child, this first band matches Mary, who is the mother. This second band matches Larry. This third band, well, Bob and Larry both have this band. So, and then this band matches Larry. So this band more than likely came from Larry, right? So the banding pattern shows that Larry is probably the father. And they give like percentages, you know, it's 92%, or, you know, probably because of this situation. You couldn't, like 100% would be hard to say that, but you have to just look at each band. So now let's look at this one. Here's the mother, here's the child, here's two males that could potentially be the father. Who do you think the likely father is based on the banding patterns?
Male one.
Okay, so let's go through. Here's the child, so male one, they both have that band. This came from the mother, this came from male one, mother, male one, mother, male one, male one. This could have been either the mother or male one, this and that. So you see how every band's accounted for, either from the mother or from the potential father. So you have to kind of look at multiple different things and piece it together. So the paternity is going to be a little bit more complicated. So you're going to figure out who's the father of Honey's kittens, okay? Who's the father of Honey's kittens? No judgment, right? I mean, she's a cat, nature, so just throwing that out there, right? It's okay.
Let's not shame her.
No shaming, no judgment. This is just a simple biology experiment, right? Biotech at its finest. We can do this, you know, not to make her feel bad, just so we can figure it out. And so here's the scenario. Mary's cat Honey disappeared for a few days. She started gaining weight, eating more. That actually happened to my cat when I was young. Our cat Fluffy went out, she started gaining weight, but she was so fluffy that we didn't even notice that she got bigger. And then one day I went to my bedroom and she had her kittens in my closet.
Aww.
Yeah, you know, and I'm like, Mom, there's all these kitties in my closet. I was excited, and my mom was just like, oh,
great.
And so actually one of our cat's kittens, his name was Oreo. My parents had him just since till like last year. They've had the kitten of Fluffy, our childhood cat. So yeah. Anyway, couple months after she disappeared, she did find cats in her closet. This happened to us. But who's the father of the kittens? We don't know. There's lots of cats that can roam. And so here's Honey. Here's the 4 kittens, okay, cream, molasses, ginger, and sugar. You notice that they do have different phenotypes, right? They have different fur color. And you can see Honey. You can see what her phenotype or physical traits look like. Here's the potential fathers. These are just the 2 that were in the neighborhood, right? These were the 2 that she knew hadn't been neutered. So here's Tom and here's Bob. They do look somewhat similar. You know, but they do have slightly different phenotypes. And so you could potentially make a hypothesis based on the phenotypes without really doing the experiment and maybe saying, you know, if you're looking at these kitties, who do you think the father is? Just making a phenotypic guess, right? I mean, the other thing I need to mention is that cats can actually be impregnated by more than one male. So the kitties don't necessarily have the same father. Because remember that cats are in heat and they're fertile for a set amount of time, right? Maybe a couple of days. And so if they can get impregnated during that time from multiple males. So you have to keep in mind that Honey's kitties may not have one father. They may have like each cat could have its own father. Some of them may be siblings, some of them may not be siblings, okay, or half siblings, but maybe not full. So that's another thing to consider, because the kitties have their own little sacs. I mean, I used to teach anatomy and we used to do cat dissection. So although we thought we had male cats, what we found out is that no, the company that sends the cats out was wrong, and we were surprised, and we, you start the dissection and you're like, oh boy, but yeah. So anyway, you'll see like the little sacs with each little kitty, and so it's not just like one loop that's in the cat, they're separate, okay, they're separate. And so it's going to be a little bit more complicated in that it's not going to be as simple as like, oh, they're all Bob's kittens, oh, or they're all Tom's kittens. They could potentially not even be Tom or Bob's kittens. Those are just the two cats that we know of, okay? Because yeah, cats roam, and with cats in heat, it attracts attention to itself, right? The other cats know that it's the opportunity, okay? And so here's the profile of all of them, Tom and Bob. Here's the cats, and so I'll let you kind of look at that for a second. And I can put this up later as you're actually looking at your DNA, but you can kind of look at this and make an educated hypothesis just by looking at this. That's what I would do, because you're going to need a hypothesis for this experiment. And so for this, you'll need a hypothesis. For the crime scene, you don't really have any other data to help you make an educated guess as to who the suspect will be. But this you can. So you might want to just jot down who you think is whose father. Do you think Tom is the father for all of them? Bob the father for all of them? Do you think Bob's, the father of certain kitties? So I would just look at this and write a couple notes down so you can write that hypothesis for yourself just based on visual observation. So go ahead and do that for a second, and then I'll move forward. Ooh, hurry, I'm gonna talk too long, we're not gonna finish.
Oh, yikes.
Hey, thank you. Oh, they have, okay, these ones don't have anything. I knew that one of them didn't have letters, so. Okay, did you guys take a look? Write down, make a guess. Guys, this is a guess. Do the best you can, okay? All right, so obviously we needed DNA and biotech to solve this. So she can take a little bit of their cells, and so maybe she took some of their fur. They have to extract the DNA out and do a molecular analysis, run a DNA gel. And so what you're getting today is just the samples, okay? You're getting the samples here, okay? And we're gonna give you the tubes. And so you need to keep them separate because they all have colored labels, and so there's gonna be a set for crime scene and a set for the fraternity. And I'm gonna write this up on the board for you guys. So make sure you keep all of your samples organized, don't mix them. The fraternity has letters on them. The crime scene is just color-coded, no letters. That's another way you can keep them separated when you're doing this. And so they took the fur, the hair from each cat, they carefully labeled them, extracted DNA, and they used PCR in this specific situation to amplify certain regions of the DNA well, they'd have to have Bob and Tom's DNA and Honey's DNA as well, and the kitten's DNA, and then they performed an analysis, okay? And so you're going to run that DNA out on a gel and determine what happened. And so this is just a little picture. I'm gonna have you guys use your micropipettes and load 5 microliters of each sample into an individual well for yourselves. And then you're going to run them out, and it takes about 15 to 20 minutes to separate out all the bands, and then you're going to take your gel out and put it on a white background and take a picture of your gel, okay? And so you should get something that maybe looks like this. You'll see like different banding patterns, like yellow, orange, blue, blue. You'll see patterns for each cap, and it'll be a little crisper than this once you run them out. Okay? Dad, is that you? Then you'll look at your results. Then you'll look at the results and determine, based on the banding patterns, you need to say, okay, Tom is the father of molasses, Bob is the father of cream, whatever it is, but you're looking at the data. The data is what's going to give you that information. And so I put a different chart there just so you could kind of write in your lab. You'll have to write the kitten's name and then the father based on DNA comparison and then just kind of why. And so make sure you write that stuff in. Okay, the last thing I want to show you is just a really quick video to show you how to use your gel box. So here's a video for you guys.
Oh, Grace.
The new mini one system. And we are going to go ahead and unpack the student station box. And it contains a photo hood, the gel buffer tape, the carriage, the casting stand tray, and the power supply cord, a funnel, 2 gel platforms, a black and a gray, your P20 pipette, and a laminated sheet with practice micropipetting.
You will also need a bottle of the appropriate 1x running buffer. Be sure that you use the same buffer to make the agarose gel and to run the gel.
Okay, so that's important. So it says, be sure you use the same buffer in your gel that you use to make the gel. So Albert already made the gels and he used SB buffer to make your little agarose gel. That's why we're using SB buffer today. If he would have used a different buffer, let's say TAE buffer to make the gels, then we would need to make TAE buffer to use. So the buffer always has to match up. Whatever you use in the gel, you use the same buffer in that gel box to run your samples. If you mix, it's not gonna work. Like you can't make a gel using SB buffer and then put TAE buffer in the gel box. Okay, that's a no-no. Or you can't make a gel using SB buffer and pour water in the gel box. Okay, so that's a really important point. And notice they already are using 1x buffer. You're gonna make that for yourself today.
Please watch our other video to learn to dilute concentrated stock buffers. Let's set up the electrophoresis unit. Note the gold rivets inside the carriage is where the electrodes will need to make contact. Do not allow liquid to get into the black carriage. Be careful to plug in the power cords straight into the hole at the back of the carriage. Do not hold it at an angle. Make sure that your electrophoresis unit is in the desired location, as the unit should not be moved or bumped after you start loading the samples. This is the gel buffer tank. The negative and positive signs are imprinted on the bottom. On the buffer tank, one side is smooth, and the other side has external bumps, which are the electrodes. There is a gel tray platform that can hold a black plate for DNA samples, or a gray plate for color dye samples.
So you guys should use the gray plate today because we're using colored dye samples. We're not giving you full-on DNA today because I just want to make sure that you can load gels, run them, and analyze them. So use the gray tray today, not the black one.
Notice that the plate has a little knob underneath, which only fits one way into the buffer tank. Match the ridges of the gel tray with the buffer tank.
Did you hear that? It says match the ridges of the gel tray with the buffer tank. There's only one way that tray can go in. There's 2 little ridges. Did you see me? I was even looking at it and trying to figure directionality out. If it doesn't just drop in, it means you have it backwards. Do not try to shove it in because then it's really hard for us to get it out and we might break the gel box. So look at the 2 rivets, match them up, and it should just drop right in. If it doesn't, you're doing it wrong. It's backwards. Same thing with that tray, that little notch underneath. If you're putting it in backwards, you're gonna really have to be shoving it in there. If it's very difficult, it's because you have it the wrong direction. So don't force anything or you're going to break the boxes.
The gel tray will only fit into the buffer tank in one orientation. Place the gel tray containing an agarose gel on top of the plate. Make sure it is flat against the gel platform. Check that the wells are closest to the negative side of the buffer tank.
It's important.
Carefully, place the buffer tank straight down inside the carriage.
And push it
Check
down.
that the top
so it
edge
snaps
of the
in.
buffer tank is level, and that the electrodes are making contact with the gold rivets in the carriage. Measure and pour in 135 milliliters of 1x running buffer into one side of the buffer tank. Watch to see that air bubbles will move under the gel tray to the other side. You can move your funnel to the other side of the buffer tank. Be sure that the buffer completely covers the gel, but does not exceed the buffer fill line.
So the liquid buffer should fully submerge the gel. So there should be about a millimeter of liquid above the gel, and so make sure there's liquid on both sides. I know it said 135 milliliters, but you can just kind of pour. You don't need to measure out 135. Take your funnel, pour, and just fill it up on one side, then let it kind of move over to the other, start on the other side. Make sure the liquid, if you see any notches or the edges of the well, there's not enough buffer in there. Okay, there is a line that's a buffer fill line. Depending on the thickness of gel, sometimes we have to exceed the buffer fill line by just a little bit. So it's more important to make sure the gel is completely covered than to just go by the buffer fill line. Because depending on who made the gels, they may be thicker or thinner, which then displaces the buffer differently, okay? The other thing is make sure you use the funnel. If you get any buffer outside of that container, like if it falls in where those little metal rivets are, your gel box is not gonna work, okay? It will just not work, and it'll be really hard to get it to work. So do not get buffer in the edges around the actual tank.
For DNA samples, use the low light and black plate to load your samples into the wells. For color dye samples, use the gray plate.
And so do you see what they're doing? They're putting the tip right over the well, and then they're dispensing in. And so you do not need to put the tip in very far. So if this is, your well, and this is your tip, you just need it like right over the well, because there's glycerol in those samples. So the minute you dispense, the glycerol is more dense than the buffer, so it makes the sample sink to the bottom of the well. Okay, so you don't need to be like fully in there. You just need to be sitting right above the well, or just slightly, the tip just slightly inside of the well. As you dispense slowly. Okay, do not let your thumb off of that button, off the plunger. You need to dispense, lift it out, and then you can release on your thumb. If you dispense and you release your thumb while the tip is in there, it's gonna suck your sample plus buffer up, and now you've just mixed the sample. And then if you try to dispense, now the density is not correct anymore, so that sample may just spill right out of the well. Okay, so it's very critical. Dispense, lift out, and then release your thumb. Okay, you might want to practice that.
When we do that, do we go to the second stop?
So the problem about going to the second stop is that you might release air and it'll blow the liquid out. Okay, so I like to go to just the first stop with gels. I would stop at the first stop and that's it. Do all of them the same. Because that last little push, what's happening, you're blowing air out, it'll blow bubbles out, and then it might displace your sample out. Or it might even just displace it enough in the well that your bands look smiley. They have like extra DNA on the sides and not as much in the middle. So I would go to just the first stop for gel loading, okay?
Please watch our other video for tips about loading gels. Place the hood onto the carriage. Push on the power button. A steady green LED light will show that the power is on.
If this gives you the flashing green lights of death, please let us know immediately. The boxes are a little finicky, and so if you made your buffer incorrectly, that might happen. If you get liquid, if you get like the liquid buffer in here, so if you're pouring and any of it gets where those electrodes are, it won't work and we'll have issues. So just be really careful. Sometimes you do everything right and it still doesn't work. So we'll cross our fingers that today's a good day and everything goes well. Okay, but just if this is flashing, you need to let us know right away so that we can help you.
If you have DNA samples, it is important that you do not leave the light on while the gel is running, or the light-sensitive DNA stain will quickly fade. If you move the hood off the carriage, the power will automatically shut off. After replacing the hood, be sure to check that the green light is on. If not, push the power button again. Within 2 minutes, you should see bubbles forming on the negative electrode, which indicates that there is an electric current flowing throughout the buffer.
See the samples are separating out?
If separating DNA samples, watch that the loading die is moving towards the positive electrode.
So what would happen if you put your gel in the wrong way? What if you put the DNA at the negative electrode, at the positive electrode instead of the negative electrode? It'll run, but in the wrong direction, right off your gel. So you always need to make sure that the DNA, the wells and where you're loading is at the negative side. If you put it in backwards, it will just run right off the gel and into your buffer and your sample is lost. Okay, so just be sure that you're doing it in the right orientation.
Usually, we will check the gel every 5 minutes. The new hood design has vents to prevent condensation. Place your phone camera flat on top of the photo hood. Do not use the zoom feature, as the hood is already at the best focal length for a smart device.
So today you're using dye, so you're gonna need to just take the gel out, put it on, there's this little white card. So because you're using dyes and not fully DNA today, take the gel out, place it on this so there's a nice white background, and take a picture of your gel. Okay, I can even get the little expo markers and you could even label and then put your gel on there if you like. And so in a few days we'll actually use DNA and the fluorescent dye, in which case then you can do this. You can take pictures with your phone. And we'll even use the better. I have a nice camera, an imager over there that's even better, but we'll do both. But today,
If you have DNA samples, use the highlight setting and check that the fluorescent ruler is visible in your photo. Turn off the blue light as soon as your photos are taken. Usually we run samples for about 15 to 20 minutes. Turn off the power when the dye front has moved towards the positive electrode, but before the dye runs off the gel. If you have a separate blue light or UV transilluminator, you can also transfer the gel to take the photo under the transilluminator. If you have colored dye samples, transfer the agarose gel onto a white laminated sheet to photograph.
So that's what yours will look like. You'll put it on that laminated sheet. Today it's just dye with no DNA, but it still gets the idea across. And then next time, and probably by Wednesday, you'll...
Usually, we dry off excess buffer around the gel and use an expo marker to print the lab team name and sample names above the wells. If you have used gel green stain, it is safe to discard the agarose gel into a regular school trash can. We hope that this video has helped you learn how to use the new Mini 1 electrophoresis system.
Okay, so are you guys ready? I gave you a lot of information. So what you need to do now is make your buffer first, because you need it to set this up. Once you've made your buffer, then go ahead and let us know. Albert and myself will come around and give you your gels. And we can also give you a little practice gel if you want to just practice loading a couple of times into the practice gel just to see what it feels like. We can also come around and demo kind of to your group or to your table exactly how to load. Okay, so go ahead and start making your buffers, and Albert has you've already given out all the samples?
Yeah.
So Albert's already given out all the samples, and I will write on the board the order in which you need to load them, and I gave you like a little table so that you can write it in and make sure you have them in the correct order. So while you're making your buffer, I will write the loading order on the board for you guys, okay? So get your lab coats on, get your gloves on, and get to work. And if you want to double check your math with Albert or myself, just raise